Alrighty, lads and ladies, welcome back to college algebra. Excuse me. So we are a few lectures into our little experiment here with logarithms, and today we're going to continue talking about logs and exponentials from a slightly different perspective than we have been. So last week, the focus was on just sort of trying to get to know the logarithm functions, in terms of sorting out inputs, in terms of outputs, sorting out outputs in terms of inputs, and playing around with the algebraic properties, those sort of identities, if you will, that the logarithms obey. Today, we're going to see sort of the real utility of these things. We've gotten a small taste of that from the previous homework set. There was a little bit of equation solving, but today we're going to dig in much deeper with the equation solving. So we're going to talk about logarithmic and exponential equations. Let me go ahead and turn on the screen sharing. Take this up. And we'll pull up your homework set so we can have a few examples to look at that come straight out of there. Okay. My son is home from daycare today because he's sick, so I apologize for the background noise. This is MAC1105 section 0, which is college algebra. And the date today is the 5th of April, 2022. And today, we're going to talk about log and exponential equations. So you'll remember that when we first introduced logarithms, kind of the primary motivation was that equation 2 to the x equals 3. We could see from the graph that there had to be a solution. We were even able to approximate the solution pretty accurately using a calculator. And then we got lots of practice with that in the following homework sets, slightly different exponential equations. And I've promised this whole time that we're going to get to a place where we can solve these things exactly by hand. That's the main goal of today. So the big idea is to solve equations of the form. And I'll give a log equation here and an exponential equation here. I'm going to abbreviate exponential as exp. So an exponential equation is one like, b to the x equals something, let's say c. And a log or logarithmic equation is something like log base b of x equals c. Now they won't look like this at first. Generally, we're going to have to do some sort of algebra manipulation, and we'll be able to reduce a more complicated exponential equation to something like this, and then solve. We'll be able to reduce a logarithmic equation to something like this, and then solve. But throughout the current homework set, your goal will be getting whatever you're given into one of these two forms, and then using the definition of the logarithm to convert these into equations that are solved for x. The main operation over here is going to be taking logs on both sides. So this usually would look like I'm going to put both sides of the equation inside the logarithm. So here I would have the log base b of b to the x, and over here I'd have the log base b of c. And I mentioned in the past that we will not always use the base logarithm that matches the thing over here. In fact, I'll pretty much always use the natural log. But the end result is that then by a property of logarithms, right, that the log base b of b to the x always simplifies to x, we'll get x equals the base b log of c. And there will be some, like I said, some variation on this. I will use different base logarithms when doing this from time to time, because you usually want to, if you get your answer in this form, you want it in a form that you can kind of plug into your calculator to get a decimal approximation for that number, because while this would be your exact answer, it's hard to say how large or small that is. So this is the sort of general recipe for solving exponential equations. And the big move here is we're learning a new verb. We're learning a new operation, and it is take logarithms. The new operation over here is to exponentiate on both sides. So to solve an exponential equation, you take logs. To solve a logarithmic equation, you exponentiate. The idea is to do whatever undoes the thing that's hiding your variable, right? Here, the variable is trapped inside the logarithm. Here, the variable is trapped inside the exponential. Because the log is the inverse to the exponential function, we can get this variable down out of the exponent by taking logs. Because the exponential is the inverse to the log function, we can get the variable out of this log by exponentiating. What that means is you're going to put both sides in the exponent of your base. So c will become b to the c, and the log base b of x will become b raised to the log base b of x. And again, by our properties of exponents, on the left-hand side here, if you take b and you raise it to the log base b of x, this is plugging f inverse into f. You should just get x out. And on the right-hand side, you have your b to the c. So this is the general sort of procedure. This is what we're doing. The properties that work here are that this will always simplify to this. So b raised to the base b log of x, by definition, will always just be x, because b to the x and log base b of x are inverse functions. And the main property at work here is that this thing is always equal to x. That when you take the logarithm base b of b to the x, that will also always simplify to x. I mentioned that when solving exponential equations, taking logs, I will often use the natural log rather than the base b log. Over here, when solving logarithmic equations by exponentiating, we always have to exponentiate using the base of the logarithm that's given. All right, that's a lot of talking. Let's look at some problems. We can start simple. How about something like this? So this is almost in that form we discussed, right? Like some number to the x equals some number. It's very, very close. And we could start fiddling around with the left-hand side. I could write this as 5 to the x times 5 to the negative 3, and then push that 5 to the negative 3 over to the other side, dividing. But we can go ahead and take logarithms here, and I think that's the nicer move. So we're going to take base 5 log of both sides. This will give me the base 5 log of 5 to the x minus 3 equals the base 5 log of 11. And then the big deal here is that the base 5 log of 5 to something will always just be that something. So if you like, the more general way of writing that rule is that the log base b of b to some stuff will always just be that stuff. So on the left-hand side, the base 5 logarithm of 5 to the x minus 3, that's just x minus 3. On the right-hand side, there's no escaping this. This is just the base 5 log of 11. And then if I give you this, remember, this is just a number, right? The base 5 logarithm of 11, it's the number to which you must raise 5 in order to get 11. It's a weird number, right? I don't know exactly what the number is. It's a little bigger than 1 because 5 to the 1 is 5. It's smaller than 2 because 5 to the 2 is 25, but it's a number. Most importantly, it doesn't have any x's in it. So if I'm trying to just get x alone, the only thing keeping that from happening is this minus 3 over here. So I can add 3 to both sides. And I get x equals the base 5 log of 11 plus 3. Questions on the procedure? I have a question for you. Is this equal to the base 5 log of 14? Right, because 11 plus 3 is 14. I've got the base 5 log of 11 plus 3. Is that the base 5 log of 14?
No.
No, that's correct. This is not the same. And you remember when I talked a little bit last week about how important it is to put parentheses around the inside of the log? This is why. Right? It's very easy if you didn't write these parentheses to think that the 3 is being added inside the logarithm, but it's not. Now we can check with our calculator. We've got some doubts. Oh, but first we would need to convert this to a natural log. So real quick here, let's say. No. All right. If I want to write this in a form I can plug into my calculator, right? This is good. This is the exact answer. And we can stop and declare victory here, but I don't know how big that is. Is that like 7? Is it like 4? Is it like -2? It's not at all clear to me how large or small this number is. So if I want a decimal, if I want a number that's kind of easy to get a feel for the size of, then I would need to put this into a calculator. And the way to do that is using the change of base formula. because when you look at your calculator, you have an ln button here, and you have a log button here. This is the base 10 log that first homework set was riddled with. This is the natural log, or the base E log. So I could say, according to my change of base formula, this is the same as the ln of 11 divided by the ln of 5 plus 3. Remember, we had those two special cases for the change of base formula that we use a lot. You can either kind of get comfy using the natural log or get comfy using the common log. This I can now put into my calculator. It's the natural log of 11 divided by. Make sure you close those parentheses before you hit the divide. Otherwise, it's going to think you're dividing inside the log. Divided by the ln of 5. Enter. So this number is about 1.48. That's the base 5 log of 11. And then I add 3. We get 4.489, blah, 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 blah. Call it 4.49. Okay. Now, I don't know about you. I don't like having to memorize lots of formulas. The change of base formula is useful for sure, especially when it comes to calculator stuff, but wouldn't it be nice if I could get this answer right away? So this is also an exact answer, right? It's just a different form of the exact answer. This is the decimal approximation. You could argue that this is a cleaner looking exact answer, and you're right in a sense, but this is the form that has more utility because this is the form that you can plug into your calculator. So for us, especially in this class, it would be cool if we had an equation solving process that kind of led us naturally to this form of the exact answer rather than getting to this and then using the change of base. So I'm going to solve the same equation slightly differently. And then from here on out, I'm going to solve all exponential equations in that way. Now, before I do that, are there any questions about any of the steps here? What we did, why we did, how it worked, anything like that? Okay. So same exact problem. Solve 5 to the x minus 3 equals 11. This time I'm going to begin by taking the natural log of both sides. And it might seem like this isn't going to work out the same way because the base here is 5, but we'll use some slightly different properties of logarithms to get ourselves to that answer. And then we won't need the change of base formula. So if I take the natural log on both sides, I'm going to get the natural log of 5 to the x minus 3 equals the natural log of 11. And now the property of logarithms I'm going to use, this is not just going to simplify to x minus 3. Right? Because the logarithm here is not base 5. So they don't cancel in the same way that the other ones did. But I can take this power here and flip him down here. That'll give me parentheses x minus 3 times the natural log of 5 equals the natural log of 11. So the rule or property that I'm using there, remember, is one of those rules for logarithms. That log base p of x to the y is y times the log base p of x. All right, you can always bring a power inside the logarithm down in front. You do want to make sure that you put this whole thing here in parentheses here, because this whole thing was the power, which means this whole thing is multiplying ln5. Easy mistake to make, forgetting those parentheses. But from here, things are very quick. Natural log of 5, just a number. I want to get x alone. So I would start here by dividing both sides by the ln of 5. And you get the ln of 11 over the ln of 5. And then you add the 3. That's it. That's your exact answer. Same as we got last time, but now it's already in the form that you can plug it into your calculator. In truth, this is what all mathematicians do when we solve these equations. I can't think of anybody who would look at this and go, take the base 5 log of both sides, because nobody uses base 5 logarithms. Everybody uses the natural logarithm all the time. Questions on these steps or anything that we did here? Okay. Let's take a look at a more application-centric problem. This first one is fine. I'm going to modify it just a little bit. So I invest $300 at 5%. The interest is compounded monthly, and I want to know how long is it going to take for my investment to double. The game here is to begin with that compound interest formula and then set up an exponential equation, and then finally solve that exponential equation using logarithms. This is very much the sort of thing that we were doing last week, but the exponential equation that we got at the end, we would solve by using the table and the calculator. So my recipe for compound interest says that the amount after x years will be p times 1 plus r over n raised to the nx. People sometimes use the variable t here because t pretty much always represents time. It doesn't matter. P is the principal. It's the initial amount. It's the amount that you're investing or borrowing at the start. That's $300. 1 is 1. R is your interest rate, which here is 5% as a decimal. That's 0.05. And N is the number of compoundings per unit time. So we're measuring time in years, compounding monthly. There are 12 months in a year. So here's my function. I'll write down the values of these constants on the side. P was 300. R is 5% or 0.05. N is 12 because there are 12 months in a year. Okay, this is my function. What I want to know is how long is it going to take this investment to double? So what will the amount in my account be when the investment has doubled?
600.
Yeah, I originally invested 300 bucks. So I want to know, when is this thing going to reach 600? So that's the equation we're going to set up. I'm going to set this apparatus equal to 600. My goal is to get X alone. And there's a lot of stuff in the way of that. Kind of the outermost thing that's going on over here, we want to think of it like an onion, you know, you're going to peel the layers off. The outermost thing that's going on over here is this multiplied by 300. So to get rid of him, I'll divide both sides by 300. 600 divided by 300 is 2. You can simplify the inside here, right? This 1 plus 0.05 over 12 is just a number. My only warning there would be, if you're going to simplify this and write it as a decimal, make sure you give yourself a lot of decimals, because this function is very, very sensitive to the base. If this thing is off, if this base is off by just a little bit, that will change this function, the speed at which this investment grows, by a lot. So you don't want to round to 1 or 2 decimal places. If you're going to do that, you want to round to like 8 decimal places. Give yourself a lot of precision. For my money, I'd just leave it like this, at least for now. So here what I have is some number. Oh, sorry, this mouse is sticking. On the right-hand side, I have some number raised to a variable power is equal to, on the left-hand side, I have just the constant 2. So if I want to get this X alone, I need to get it down out of the power. That's now the outermost thing going on, is this 12X up here. So I will take logarithms on both sides. That's the game. We're going to take logs. And I'm going to take the natural log on both sides. The left-hand side, there's nothing to do. The natural log of 2 is just a number. It's like 0.69. On the right-hand side, I have a log and then a power inside the log, right? Everything in here is being raised to this power. So I can bring that power down in front. The natural log of 2 is equal to 12x times the natural log of 1 plus 0.05 over 12. If I'm being careful, I suppose. the same property we used. Just bring this power right. I can divide over by this number. And now I'll just have 12x. And then finally, to get x alone, I also need to divide by the 12. So give me the natural log of 2 divided by 12 times the ln of 1 plus 0.05. So this is our exact answer in terms of logarithms. And if I want a decimal approximation for this answer, I can type the natural log of 2, close parentheses, and divide by. And now I'm going to open up parentheses downstairs in the calculator because I'm going to type all of this stuff. And I want to make sure that the calculator puts all of that stuff in the denominator. So open paren, 12 times the natural log of plus 0.05 divided by and close. I get 13.89. So with this interest scheme, right, 5% compounded monthly, it would take close to 14 years for your investment to double. The sad truth is that most savings accounts right now are way below 5%. Like we're talking 0.03% interest or something, right? Which would be 0.0003 as a decimal. So savings accounts are really not wise ways to invest these days. Mutual funds, I think, pretty close to about 5%. Some stocks. Another fun game to play with these. If you haven't done this, I don't know if any of you have student loans, but go ahead and see how long it's going to take for your student loan amount to double if you didn't make payments. See how quickly the interest there goes up. Or credit cards. If you have credit cards, the APR usually right around 20%, maybe a little lower if you have great credit, maybe a little higher if you have less than great credit. You'll see that those rack up much, much faster than any sort of savings account. Questions on any of these steps? Okay. So all of the problem types that we were doing last week with the calculator, we can now solve exactly. There's lots and lots of stuff. I want to pivot now to talking about logarithmic equations. Or maybe we can take a look at something a little. Yeah, maybe before we go to logarithmic equations, let me take a look at something a little bit more challenging. One more. So 23 to the 6x minus 15. 23 to the There is more than one way to skin this cat. This is an exponential equation. So I could, in theory, begin by taking logarithms on both sides. But well, let's just see what happens if we do that. This will work fine as long as you're very careful about it. On the left-hand side, I'll get parentheses, 6x minus 15 times the natural log of 23. And on the right-hand side, I'll get parentheses, 4 minus 5x times the natural log of 23. And then if I divide both sides by the natural log of 23, 6x minus 15 equals 4 minus 5x. And kind of the thing you're meant to realize is that you could have gone straight from here to here, because both sides are 23 raised to some power, 23 raised to some power. So the only way for that to be possible, for those two things to be equal, is for the powers to be equal. In general, this is called the one-to-one property. And it's a convenient way to solve exponential equations quickly when both sides are just some base raised to some power, and the bases are the same. So if you have like b to the x equals b to the y, that can only be true if x is equal to y. So 23 to some bullshit equals 23 to some other bullshit means that the two bullshits have to be the same bullshit. Right, so certain exponential equations, this can be a really fast path to solve them. You can do it without ever touching a logarithm. That's sort of the idea. But it only works for these types of equations, where you've got same base on both sides, raised to some powers on both sides, and nothing else going on. From here, I'll add 5x to both sides. So I get 11x, 15 equals 4, 15 to both sides. X equals 19, and then divide both sides by 11. No calculators needed, no logarithms needed, if you want. Right? This step here with logarithms was unnecessary. We could have just come down to here. There is one other type of exponential equation that I'd like to discuss, but I didn't see it when I was looking through your homework. I wanted to go a quick careful look to make sure I didn't miss it. But, no, okay. Well, they got rid of those. All right. No harm, no foul. Any questions on what we did here? Okay. The counterpart to exponential equations are logarithmic equations. And as I mentioned at the start, the way to solve those is to kind of isolate the logarithm and then exponentiate. So just like with exponential equations, we isolate the exponential and then take logs. Logarithm equations, you isolate the log, then exponentiate. So we'll start simple. All right, in a logarithmic equation, your variable is trapped inside a logarithm. Here, the log is already isolated for us. Right? There is nothing multiplying the log. There's no addition or subtraction going on outside the log. I just have log of some variable stuff equals a constant. So our first step is to exponentiate both sides using base 2. So this is a new word for us. It just means to put in the power of. It's different than raising to the power. I'm not going to square both sides. I'm not going to raise both sides to the power of 2. I'm going to raise 2 to the power of each side. So it is a totally new operation. We will get 2 raised to the base 2 log of x plus 1 equals 2 raised to the power of 7. Now on the left, I've got like b raised to the base b log of some stuff. That will always just simplify to the stuff. So the left-hand side is just going to become x plus 1. Yeah, x plus 1 equals 2 to the 7. And the property there is that b raised to the base b log of some stuff. This always just simplifies to the stuff. Here it does matter that the base here is the same as the base here. So when we're solving exponential equations, I always use the natural log because it's kind of a time saver in getting me to that form where I can plug it into my calculator. With exponential equations, we don't have the same flexibility. There is no nice property of logarithms that says like b raised to the base a log of some stuff is some stuff, or any sort of nice way to simplify things like that. So I have to use the same base when I exponentiate as the logarithm I'm trying to undo. Well, that gets me here. Great. Now all I have to do is subtract the 1. It happens to be the case that 2 to the 7 is 128. So this is 128 minus 1, or 127. That's my answer. This is 127. If you don't know that 2 to the 7 is 128, of course, you could use your calculator. Questions about any of these steps?
Do you use 2 for any problem like that where it says exponentiate both sides using base 2? Do you do that for any, or would you use whatever base is showing?
I have to use whatever base was given to me. So if the logarithm given was a base 2 log, I'll use base 2 when I exponentiate. If this was a base 5 log, I would use base 5 when I exponentiate. If this was a natural log, I would use the base e. So yeah, that's worth writing down. We said it, but let's write it down. So if my variable is trapped inside of a base 7 log, I have to exponentiate both sides using base 7. If my variable is trapped inside of a natural log, I have to exponentiate both sides using the base e. We don't have the choice of the flexibility here that we have with exponential equations, unfortunately. Good questions. Other questions or thoughts on this one? Okay, let's step it up a little bit. Again, the kind of idea is to isolate the log term, then exponentiate. So I'd start by adding 3 to both sides. Now I've got the log all alone. My variable is stuck inside of this logarithm and there's nothing else going on over here. So I'm ready to undo the log, which means I need to exponentiate. What base will I use here?
1.
Not 1. What is the base of the natural log?
10.
Not 10. It's a special number. It's that number e. That Euler's number, 2.718, blah, blah, blah. So what we need to do is exponentiate on both sides using the base e.
I thought whenever there wasn't like a base that was presented, you would use 10 as the base.
If you have log without a base, so the other special base logarithm, the other special notation is the log with no base written, and that is the base 10 log. It's in the kitchen. I thought it was still in here. So the natural log, if you see ln, that means we're talking about the base e log. If you see log without something written, that means we're talking about the base 10 log. So here we've got an ln. That means we're talking about the natural log or the base e. So we'll use that number e to exponentiate on both sides. So then e raised to the ln of 2x is just 2x, because this is like e raised to the base e log of 2x. In your mind, you can always replace ln with log sub e. And if you want to write it that way, to keep it straight in your head, that's okay. There's nothing wrong with doing that. On the right-hand side, e to the 8 stays e to the 8. And then finally, I can divide both sides by 2. When we solve exponential equations where the base is like an integer, like base 2 log on the last one, or base 5 log, or common log, base 10 log, your answers are generally going to come out pretty nice as rational numbers. When you're solving a logarithmic equation where the base is e, like a natural log like this, your answers are most likely going to come out in terms of that number e. So just like with the exponential equations, here you'll usually want to give a decimal approximation here. E to the 8, how big is that? You have to think about it for a minute. E is kind of between 2 and 3, a little bit closer to 3. So e to the 8 is somewhere in the neighborhood of 3 to the 8. It's a big number. But to see exactly how large this is, we're going to hit the second and then the ln button, and that's going to give me e to some number. Or if you wanted to, you could type second and divide. That will also give you an e, and then you hit the caret to get up into the power. Either way, e to the 8 is about 2,980. And then we need to divide this number by 2. And we get 1,490.48 if we're rounding to 2 decimal places. And this would be your exact answer. This would be your decimal approximation. Questions on any parts of this? Notation, steps, algebra, anything? Okay. The procedure for these equations is not terribly hard. Let me give you some really basic steps for each. So your first step is to isolate the term with the variable, meaning either isolate the log or isolate the exponential. Then you're going to undo whatever is trapping the variable. So if your variable is inside a log, you're going to exponentiate using the base of that log. If your variable is in a power, if your variable is stuck up in an exponent, then you will take logs on both sides. I should add on both sides to the first one too. And with the exponentials, if your variable is trapped in an exponent, then you could use whatever base logarithm you want. I suggest the natural log. Because using the natural log, your answer will come out in a form that you can easily plug into a calculator without having to rely on the change of base formula. This is almost the entire story. I do want to talk a little bit about domains. In both exponential and logarithm equations, it is possible that there is no solution. And in logarithm equations, it is possible that you get multiple solutions, but one of them isn't correct. Even following the correct algebra steps, it is possible to end up with, say, two solutions, one which works, one which doesn't. Let's talk about the exponential stuff first, because that's a little simpler. The domain of the base b logarithm, where b is any possible base, is the interval 0 to infinity, i.e., you can't take the log or ln or log base 2, blah, 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 of 0, -1, -3/2, any number that is less than or equal to 0. You can only take the log of a positive number. Right? The domain of all logarithm functions is just 0 to infinity. This is where the problem comes in. If you try to, say, take the natural log of 0, you're going to get a domain issue. If you try to take the log of -3, you're going to get a domain issue. So these are not defined, right? And it's not just ln and log. Any base logarithm, you're going to run into this problem. The other thing is that when solving somewhat complicated log equations, we can get what are called extraneous solutions, where you solve normally, get, say, 2 solutions, but one of them makes the original equation undefined. Because in your log equation, you have logarithms, and maybe you get an answer out that makes the inside of one of those logarithms 0, or makes the inside of one of those logarithms negative. And we know you cannot take the logarithm of a negative number. So I'm going to show you just a couple quick examples. I don't think I didn't see any examples of the second kind showing up in your homework, which is odd. But looks like, yeah, it looks like they kind of purged the extraneous solution thing. Well, could show up on the final, probably not. I just want to make sure you're aware of this as a possibility. Quick example. This equation has no solution. I claim there is an inherent domain issue here. And you'll see it. If I take 2 to the x plus 3 equals 1, and I follow my procedure, here's the exponential term. I want to isolate that. So I'll subtract 3 from both sides. 1 minus 3, that's -2. Is there any power to which I can raise 2 to get -2 out? It might take a second of thinking. I take the natural log on both sides. Then on the right-hand side here, I get the natural log of -2. This is undefined. Does not exist. Can't take the log of a negative number. You could try to follow through. X times the natural log of 2 equals the natural log of -2, which would mean that x is the natural log of -2 over the natural log of +2. But this does not exist, right? We can try. If I take the ln of -2, I'm going to try to divide that by the ln of +2. We're going to get that same non-real answer error. All right, I'm going to get an error. the other way this sort of thing can happen, and I'm kind of shook that I don't see this in here. Yeah, no, it's not. I must have pulled it. I'm it would be a bad math teacher if I didn't show you this. So let me put down a quick example. There we go. Quick memory. I think the reason this isn't showing up in your homework is because, as I've told you, my open math, that's a new thing here at Santa Fe. I know that these exist in the Pearson version of the course, that my math lab version of the course. So I do want to show you an example like this. Because if it's in Pearson, it could show up on the phone. The way you solve logarithmic equations like this is by isolating the log and then exponentiating. The challenge here is that there's two logs and they both have the variable x inside of them. So before I can get rid of the logs here, I cannot can't exponentiate to kill the log until we isolate the log. But there's two of them. So what do we do? Is there any way I could put this together into a single logarithm, which I could then isolate and get rid of?
Would you combine the two logs into multiplication?
Yes, exactly. Equations like this are precisely why we went through that stuff with the log properties. So combine them into one. So if I have the log of x plus 2 plus the log of x minus 1 is equal to 1, I can begin my equation solving process by combining the two logs on the left-hand side into a single log with the inside x plus 2 times x minus 1. Right? Addition outside the log is the same as multiplication inside the log. Now this is a single log term isolated on the left-hand side. So we can exponentiate. Before I do that, I'm going to go ahead and multiply out the inside of the log here. So this is going to be log of x squared plus 2x minus 1x is plus x minus 2 equals 1. And then I can exponentiate. Make sure you exponentiate on both sides. Common mistake to forget. On the left-hand side here, I'll have just x squared plus x minus 2. And on the right-hand side, 10 to the 1 is just 10. This now is a quadratic equation. How do I solve this quadratic equation?
Factor it.
There's something I need to do before I can factor.
Move the 10 over.
Yeah, good, right? So if I need to set the whole thing equal to 0 before factoring will help me. So we got to subtract the 10. Now I can factor and solve. I need two numbers that multiply to -12 and add up to +1. Those are 4 and -3. So the two solutions I get out here are x equals -4 and x equals +3. One of these is extraneous. We need to check these in the original equation. You might be tempted to say, oh, well, the -4 is the problem because he's negative. It's not quite that simple. X equals 1 would also be an extraneous solution if I got 1 out, because x equals 1, although 1 is itself positive, would make this guy undefined, because the inside of the log, when you plug in 1, would be 0. So we check these in the original equation. When x is -4, we have the log of -4 plus 2 is -2, plus the log of -5, right? -4 minus 1 equals 1. These are both undefined. If you plug in x equals 3, we don't run into any such problems. We get the log of 3 plus 2 is the log of 5, plus the log of 3 minus 1 is the log of +2. This is okay. So we throw out the x equals 4 solution, or sorry, x equals -4 solution, and we just hold on to the x equals 3. I'll have to talk to the course coordinator and see if they strip this stuff from Pearson. I've been teaching college algebra here at Santa Fe for like 6 years now, and every semester I've taught this class, this content was in here. But the fact that it's not in my open math makes me wonder if they decided to yank it from the course altogether, or if it's just an error and they haven't added it into MOM yet. If it turns out to be the latter, if it turns out that they just haven't added it into MOM yet, but it is still a part of the course officially, I'll make up some worksheets for you guys with answers so you can study and make sure you're prepared for the final. But that is it from me for today. This is how we solve logarithm and exponential equations. Any questions before I let you guys go? Alrighty then, I'm going to go ahead and end it here. If there's anything you need from me, as always, you can come by office hours, send me a Canvas message, an email, anything like that. And otherwise, I will see you guys on Thursday. Take care.